So in this lecture, we'll be discussing about convex functions. So they are a very important class of functions in mathematics and have varied applications in the areas of machine learning, artificial intelligence. Usually because the functions associated with these machine learning algorithms, the squared loss function turns out to be a convex function, and hence it possesses a global minimizer. So it helps to train your model better. And to minimize the loss, then you apply various algorithms like gradient descent to arrive at that minimizer. So let us start. First, I'll give the definition of what is a convex function. So let start from the one-dimensional case only. Let I be an interval in R, and let f be a function from I to R. We say that f is convex on I if for any lambda that is non-negative and less than equal to 1, and for any x1 and x2 in I, the inequality that f at 1 minus lambda into x1 plus lambda into x2 is less than or equal to 1 minus lambda into fx1 plus lambda times fx2. If this inequality holds, then we say the function f is convex on I. This property, this expression right there is nothing but a convex linear combination of convex linear combination. That means if I have a point x1 and if I have a point x2, and if I want to travel on this line segment joining x1 and x2, the expression that can help me to go to each and every point on this line segment is this expression. In this expression, if you put lambda equals to half, because if you put lambda equals to half, it satisfies this. If lambda is half, this expression is 1 by 2, and so is this expression. So I'll be left with x1 plus x2 by 2. So I'll be arriving at the midpoint. If I put lambda equals to 1 by 3, so this would be 2 by 3 into x1 plus 1 by 3 into x2. So I will be somewhere near x1 because the weight with x1 is 2 by 3 in this case. So this is a way to traverse the whole line segment, including points x1 and x2. Because if you put lambda equals to 0, then this term vanishes and this becomes 1 minus 0, that is 1 into x1. So I end up at this point. Similarly, if I want to be at this point, what I need to make sure is I put lambda equal to 1. So when I put lambda equal to 1, this term vanishes and lambda is 1, 1 into x2. So I end up at this point. So this expression is called as a convex linear combination. So what this convex function says is, geometrically we can see let's say I have the x-axis and I have the y-axis on which I graph the function. So the graph of a convex function is roughly this shape. Why? Suppose you have a point that is x1 there. So this is x1. Let's say the point this point is x2. So you have this height and you have this height. So this height is f at x1 and this height is f at x2. Now take this point on the curve and join it by a line segment. So let's say we join it, so we get this. Now take any point on the line segment joining x1 and x2. So the general point is this. We change lambda, the point would change. So the general point is 1 minus lambda into x1 plus lambda into x2. So if this is the point, what is the height? What is the point on the curve? This is the point on the curve. And what is that point? F at 1 minus lambda into x1 plus lambda into x2. That is how you get the point on the curve. You give x, get the function value. But if you see, if you extend this line, this is also a point on the line segment, which has endpoints at f at x1 and endpoints at f at x2. So if you take this line segment, this is f at x1, this is f at x2. So this point that you get here is nothing but 1 minus lambda into f at x1 plus lambda into f at x2, because that is what we are doing. जब पॉइंट x1 x2 के नाम पे थे, तो x1 के साथ 1 माइनस लैम्डा लगा दिया और x2 के साथ लैम्डा लगा दिया. जब पॉइंट का वैल्यू बदल गया, f एट x1 हो गया और f एट x2 हो गया, और ये लाइन सेगमेंट है, तो जितना लैम्डा 1 माइनस लैम्डा यहाँ पे लिया था वही लैम्डा यहाँ पे ले लिया और लैम्डा f एट x2 के साथ लगा दिया. सो व्हाट इज द हाइट? द हाइट एट दिस पॉइंट इज दिस. So you get this height also, which is this. So if you see, this height is larger, this height is smaller. And what is this height? This value, which is on the left hand side of the expression. And what is this height? This height is on the right hand side of the expression. So what this inequality says is that the chord joining two points on the curve will always lie above the graph of your curve. So if you want to write it geometrically, it says any two points x1 comma fx1 and the other point is x2 comma fx2 on the curve if joined by a chord the chord remains above the graph of the function. So this is the geometric meaning of a convex function. You have the graph, take any 2 points, the line joining the points, 2 points will always lie above the graph. So for examples on convex functions, see the example of fx equals to x square. Just see it geometrically, then we'll show it algebraically also. This is a parabola. So this is the parabola. Take any 2 points on the parabola, this and this. The chord is above this graph. So this function is a convex function. take the function fx equals to e to the power x. So the function is this. Take any 2 points on the curve. The chord joining these 2 points always lies above the curve. Take the function fx equals to mod of x. This is the graph of mod of x. Take any 2 points, join them. The chord joining the 2 points is above the curve. Take the function x square or x to the power 4. So this is the graph. Same way we can see that take any 2 points on the graph, it remains above the graph. A function, let's say we take fx equals to x cube. So if we draw the function fx equals to x cube, it is of the shape. This is the shape. If we take 2 points, let's say we take this point and we take this point, and if we draw, this is not above because sometimes it is below and then it is above. So fx equals to x cube is not convex on the interval. Let us say the interval is -1 to 1. So it is not convex. This is convex. This is convex. These are convex. So this is an example of a convex function that is not differentiable. The rest all of them are differentiable, but this is an example of a convex function that is not differentiable. Now there is a specific shape of convex functions. It is a U-type shape. U, V, this, this. So more or less, roughly the shape of a convex function, qualitatively at least, it is U-shape, this shape. The exact opposite happens when we have something called as a concave. If you take this, if you take this function and if you reverse this shape, so what will happen? Now if you take 2 points, this point, then what is happening? पहले क्या हो रहा था? The chord lied above the graph. But now if you take these 2 points, the chord lies below the graph of your function. So when such a thing happens, you say the function is concave. So what is the definition? So concave में more or less क्या shape आता है? This. This is the shape of concave. So in this definition, if you reverse the sign of inequality, the function becomes concave. What we can say is that if f on I is convex, this implies minus of f on I is concave. So what is important is for convex functions, if this is the shape, there is always a point for a convex function below which you cannot move. For instance, in this curve, this is a point below which there is no function. For this function, if you bound this between this and this would be a point below which you cannot move. For this is the point below which you cannot move. For this x to the power 4, this is the point. So convex functions have a very, very important property that they possess a minima, which is a global minima. So let me write this. Let f from I to R via convex function, then any relative minima is a global minimum. That means convex functions cannot have this shape in an interval. This cannot be a shape because इसमें कितने पॉइंट ऑफ रिलेटिव मिनिमा है, एक ये और एक ये, और इस पूरे इंटरवल में दिस फंक्शन कैन नॉट बी अ कॉन्वेक्स फंक्शन. उसके पास सिर्फ एक ही मिनिमा हो सकता है और उसका शेप भी फिक्स्ड है. उसका शेप क्या होना चाहिए इन दैट इंटरवल? इट हैज टू हैव roughly this shape only, thereby making this point a global minima. So this you can call it as a bowl shape. In higher dimensions, this becomes a bowl shape. अभी तो U लग रहा है, U or a not so pointed V. But in general, a bowl shaped function are well behaved in the sense that they have a global minimizer. So this point is a for a convex function. This point is a global minimizer. So this is the most important property that is exploited when people train their machine learning algorithms, because the loss function that they make is a squared loss function, which is a convex function, and they train their models such that the loss eventually becomes minimized. So they are searching for this point where the loss function, this is the function, this is the loss function. ये loss function किस point पे minimize होता है, अगर ये पता हो जाए तो हम अपने neural networks को train अच्छे से कर पाएंगे. Whereas if this was your loss function, then your algorithm, when you wanted to minimize your loss function, यहाँ पे stuck हो जाता, and you might think that this is the minima, whereas in fact this is the minima, global minima. But ये problem convex functions में नहीं होती, उसमें एक ही minima है. अगर आपको एक मिल गया, so that is a global minima, not even a relative था, but वो convex function की वजह से global बन गया. So it makes sure that you are not stuck in these valleys. Now let us see how to prove that a function is convex. So let us take an example. Let's say the function is fx equals to x square, and we need to show that this function fx equals to x square is convex. So what we need to show is basically we apply the definition. What is the definition? The definition is if a function wants to be convex on an interval I, then it should satisfy that f at 1 minus lambda into x1 plus lambda into x2, the line segment, f on the line segment is less than equal to 1 minus lambda into f at x1 plus lambda into f at x2, where lambda is less than or equal to 1 and is non-negative. So x1, x2 belong to the interval I on which f is defined. This is an appropriate interval on which this is defined. So we need to make sure this inequality holds for this function f of x. That means we need to make sure that f at 1 minus lambda x1 plus lambda into x2, this minus 1 minus lambda into fx1 minus lambda into fx2 is less than or equal to 0. So now let us put the value of the function fx square, जो x होता है उसका स्क्वायर हो जाता है, तो यहाँ f के अंदर ये है तो इसका स्क्वायर हो जाएगा. तो दिस वुड बी 1 minus lambda x1 plus lambda into x2 का होल स्क्वायर, क्योंकि ये भी अंदर थी, माइनस 1 minus lambda f at x1 यानी कि x1 square minus lambda into x2 square. We need to show that this inequality is true. तो फर्स्ट वाले से स्क्वायर खोलते हैं, यहाँ से आएगा 1 minus lambda whole square into x1 square plus lambda square into x2 square plus twice 1 minus lambda into x1 into x2 minus 1 minus lambda x1 square minus lambda x2 square is less than 0. Now x1 square and 1 minus lambda can be common from this. So take 1 minus lambda into x1 square common. तो यहाँ से आएगा 1 minus lambda and वहाँ से आएगा -1. Similarly, x2 square and lambda common लेते हैं, तो lambda into x2 square common लिया, यहाँ से बचा lambda -1 plus 2 times 1 minus lambda into lambda x1 into x2. तो यहाँ से ये कैंसिल, यहाँ से lambda -1 बचा. What is left is we have to take this common, तो ये हो जाएगा 1 minus lambda. Now you can take 1 minus lambda into minus lambda common from the first two terms, तो x1 square plus x2 square यहाँ से कॉमन आया. अब सेम टर्म यहाँ पर भी है बट विद अ नेगेटिव, तो कॉमन आ जाएगा -2 इंटू x1 इंटू x2, दिखाना है कि ये नॉन नेगेटिव. सो दिस बिकम्स माइनस लैम्डा 1 माइनस लैम्डा, ये किसका परफेक्ट स्क्वायर है, x1 माइनस x2 का ये होल स्क्वायर है, दिखाना है कि ये नॉन नेगेटिव. नाउ वी हैव कम टू द एंड. सी, this is a perfect square or a whole square, so this is either 0 or always positive. 1 minus lambda is always non-negative because lambda lies between 0 and 1, so 1 is always larger or equal, so this value is non-negative. This is non-negative, lambda is non-negative, but the minus sign before that makes everything negative, so that is obviously true. So this implies this is non-negative, this is non-negative, multiplication कर रहे हो आप, this is non-negative and you're multiplying with a negative, so that makes it, that means we have to, so this implies fx equals to x square is convex. There is something more that we can conclude, which is in fact the notion of a strict convex. What is that? ये तो prove हो गया. If you let x1 not equal to x2 and lambda between strict greater than 0 and strict less than 1, so this term is always strictly negative. So this becomes strictly negative and this becomes strictly positive. So this overall thing becomes strictly negative, not even equal to 0. So when you have such a thing, you call that function as a strict convex. So in fact, fx equals to x square is strict convex. So what is the definition of a strict convex? Just take this definition, and add the condition. So यहाँ पे क्या करो? You change this to be lambda should be first of all greater than 0, less than 1, and in this the 2 points that you have taken, this should be x1 not equal to x2. So that would make them distinct. And in this, ये बन जाएगा strict. So this becomes a strict convex. Convex में क्या allow करते हैं? It is allowed that x1 can be equal to x2. The inequality can be non-strict. Lambdas can be 0 or 1 also. But in this, every part that was equal to has been removed. यहाँ से भी हटा दिया, यहाँ से हटा दिया. ये दोनों पहले इक्वल हो सकते थे, अब ये नॉट इक्वल है स्ट्रिक्टली. तो क्योंकि वो स्ट्रिक्टली है, the function becomes a strict convex function. So fx equals to x square is a strict convex function. Similarly, we can also see that fx equals to mod of x is also convex. So what we need to show, let us take this side. F at 1 minus lambda into x1 plus lambda into x2. So f के अंदर जो भी होता है उसका मॉड हो जाता है. So f के अंदर फिलहाल तो ये है, तो कैसे निकलेगा ये मॉड होके lambda into x2. Now apply the triangle inequality. So the triangle inequality says mod of a plus b is less than equal to mod of a plus mod of b. So this is mod of a plus mod of b. Now since lambda is less than equal to 1 and greater than equal to 0, this implies this term is automatically positive. So there is no need of that mod. तो ये तो हुआ 1 minus lambda. Mod बच गया सिर्फ x1 पे. Similarly, lambda is also non-negative, तो mod की जरूरत नहीं है. Mod बच गया सिर्फ x2 पे. 1 minus lambda as it is. What is mod of x1? This can be written as f of x1 because अगर x यहाँ था तो mod होके यहाँ पर आ गया. अगर यहाँ पे mod of x1 हो तो यहाँ पे क्या होता है x1. So this is f at x1 plus lambda times f at x2. So we have shown by the definition only that 1 minus lambda into x1 plus lambda into x2 is less than equal to 1 minus lambda into f of x1 plus lambda into f of x2. So this is what we needed to show for f to be convex. So this implies f is convex.